Hi everyone, I'm Tianyuan Jing. I'm glad here to present our work, Submodular with Modular Costs, Tight Approximation and Application to Profit Maximization. This is a joint work with Yu Yang, Renchi Yang, Jieming Shi, Ke Huang, and Xiaohui Xiao. In the problem, we have a union set V and a non-negative monotone and submodular function f. Submodular means that if A is a subset of B, then the marginal gain of adding U to set A is larger than the marginal gain of adding U to set B. This talk will focus on optimization of submodular functions in a cost-based setting, where each element E has a positive cost CE. And the goal here is to identify a subset S that maximizes Fs minus Cs. This problem has many real applications. A well-studied application is called profit maximization. This application is motivated by real marketing in social network. For example, Apple wants to do the advertisement for iPhone. They find some individuals in social network and put the ads with these individuals. Then these individuals spread the words. Their neighbors will be influenced first, and then a large number of people will be influenced with the network. In profit maximization, FS is expected revenue result from marketing campaign, and CS is the total incentive paid to the users in S. Then FS minus CS is a good trade-off between the benefit and the cost. Besides, the problem also finds application in sensor placement and text summarization. In sensor placement, FS is the financial benefit of installing sensors at the locations in S, and CS is the cost of installing sensors at locations in S. The FS minus CS is an ideal option for sensor placement with balanced cost and benefit. In text summarization, we are to select a set of S of words to summarize a given set of documents based on a function Fs that evaluates the summarization accuracy of S and a function Cs that returns the total length of words in S. Assuming that Fs and Cs are properly normalized, we can select a set S that maximizes Fs minus Cs to strike a good trade-off between the accuracy and length of summarization. Now review the state of the art on this problem. The first one is called simple greedy. However, this method doesn't provide any guarantee. The second one is called double greedy. Although it provides a constant approximation guarantee, it needs assumption that for any subset S, Fs minus Cs is greater than 0. This assumption is impractical. For example, in real marketing, we usually have Fs minus Cs is smaller than 0 when S equals to the union set V, as it's unprofitable to pay all social network users to be seats. The last one is called distorted greedy, which computes the distorted marginal profit gain in each round and adds the element accordingly. Distorted greedy return set S satisfies Fs minus Cs greater than 1 minus 1 over E Fs star minus Cs star. Here, S star is the optimal solution for the problem. However, there are two weaknesses. First, compared with the optimal solution S star, distorted greedy pays an extra cost linear to Fs star in the worst case, which is rather unfavorable when Fs star is larger. Further, when Fs star over Cs star is smaller than 1.58, distorted greedy doesn't even guarantee a positive profit. Now we come to our algorithm ROI greedy. Here, the name ROI comes from return on investment. The algorithm are showing as follows. The intuition of this choice of this selection rule is that it has the best return on investment in terms of the cost that we pay to add Vi into Si-1. Now we come to the proof sketch. Assume that when ROI greedy ends, we use exactly alpha times their star costs. Then follows the proof of greedy. For alpha equals to 1, greedy achieves 1 minus 1 over E approximation. For general alpha, greedy achieves 1 minus 1 over E to the power of alpha approximation. For ROI greedy, since it always adds an element with positive profit, we have the profit Fs minus Cs satisfies blue equation. And this equation achieves its minima at alpha equals to ln Fs star over Cs star. So now, by using a little algebra, we get the theorem 1. Compared with S star, our greedy incurs an extra cost that is symptotically much smaller than that of distorted greedy. Besides, our greedy yields a positive profit as long as S star is profitable. Moreover, compared with double greedy, our greedy doesn't make any assumptions on F and or C. We also show that our approximation is tight. We prove that if P not equals to NP, then for any epsilon, there doesn't exist any polynomial time algorithm whose output S is 1 plus epsilon better than our greedy. We now extend our greedy to address the profit maximization problem, where the process value of Fs for any set S is unknown, and can only be approximated with sampling. So to calculate Fs, we first need to formalize the influence model. This talk focuses on independent cascade model. In this model, each edge UV is direct and has a probability P mu V. In IC model, each newly activated node has only single chance to activate its out neighbor V with probability P mu V. Given diffusion model, Fs is defined as the number of active nodes when diffusion process ends. One of the most powerful methods on estimating Fs is called RR sampling. To get an RR set, we can first generate a subgraph G from big G, where G is constructed by removing each HE with 1 minus PE probability. Then we select a node V randomly from G. An RR set for V in G is a set of nodes in G that can reach V. This means that we can get an unbiased estimation of Fs with RR set. The following is an overview of the algorithm. We first generate two sets of RR sets, R1 and R2. Then we identify a seed set S using our greedy runs in R1. After that, we check S on condition C based on R2. For simplicity, we omit the details about the condition C here. Finally, if S is qualified or the size of R1 is larger than the maximum size, we return S. Or otherwise, we double the size of R1 and R2 and then go to step 2. The following two theorems shows the theoretical guarantees of our algorithm. From theorems, we obtain an approximate guarantee that is significantly better than those of all existing methods. We also do the experiment on profit maximization, where epsilon is set to 0.1 and delta is set to 1 over n. The cost of node is set to lambda times odd degree of node V to the power of gamma. In the first experiment, we show that for any number of assets, our algorithm always achieves the best performance on profit gain. In the second experiment, we change the cost of node by varying lambda and gamma. Again, for all settings, our algorithm again obtains the maximal profit. In the third experiment, we test the running time when the algorithm can achieve the acclaimed guarantees. As shown in the figure, compared with distorted greedy for profit maximization, our IPM obtains the larger profit while using a shorter running time. Thank you for your attention.